Hello everyone, I want to welcome you to the last video of our trigonometry series. We're going to wrap things up with the law of cosines, which is another one of the laws that allows us to solve oblique triangles, that is, triangles that are not right triangles. As I mentioned, recall that an oblique triangle is any triangle that is not a right triangle. And what we mean by solving a triangle, of course, is to find all three sides and all three angles. Last time we mentioned that any oblique triangle can be solved if we know the measure of one side and any two other parts. Now, the two other parts can be two sides, two angles, or they can be a side and an angle. But what's extremely important is that we have at least one side. There is no way you can solve a triangle if all you have are angles. We also mentioned last time that the solvable cases for oblique triangles fall into one of these categories. In the first case, you have two angles and one side, either with the side being between the two angles or not. In either case, such triangles are solvable. The other one was the indeterminate case of SSA. That's when you have two sides and an angle that is not between them. We found out that those sometimes we have one possible triangle, sometimes two, but sometimes we have no possible triangle. So to determine that, we usually find the altitude, and that helps us determine the number of possible triangles. Again, we discussed that in detail last time, so please take a look at that video for that purpose. Another case is when all three sides are known, and the last one is when two sides are known and the angle between them. Both of these last two cases are going to require the law that we're going to study today, which is the law of cosines. One thing that is nice about the law of cosines is that it either can handle a situation or it can't, and in the ones that it can handle, there are no indeterminate cases. So that's one good thing to look forward to. All right, in basically the statement of the law of cosines is that in any triangle ABC with its opposite, the three angles being named accordingly, the side opposite angle A being called lowercase a, the one opposite B being called lowercase b, and the one opposite C being called lowercase c, meaning the length of those sides, of course. What we end up with is something that looks quite Pythagorean, doesn't it? Except that because these are not right triangles, it's not going to be exactly Pythagorean. We need some adjustment. This right here is the adjustment. So, for example, a squared equals b squared plus c squared minus 2 times b times c times the cosine of a. Notice that means these are the lengths of two sides, and a is the angle between them. So you can find that the square of any side is the sum of the squares of the other two sides minus 2 times the products of the length of those two sides times the cosine of the angle between them. And this works no matter which side you start with. So let's take a look at why this works. All right, in order to prove the law of cosines, what we'll do is we'll just take a general, oblique triangle, and we'll place it at the origin, and we can do that without loss of any generality. So this simply makes the calculations that we have to go through simpler. Otherwise, any triangle can be picked up and positioned in this manner without changing any important aspect of the triangle. So if we do that, notice that we know from the definition of sine and cosine from the very beginning of the term that if this is the triangle ABC that we're looking at, then for this point C, the sine of the angle here associated with it, the angle A, which is this angle here, is going to be y over b. Remember, this is before we even got into the notion of unit circles, how we define these values for sine and cosine. These were sine and cosines of angles, not necessarily real numbers, such as is the case on the unit circle. So for sine of A, we get y over b, and for cosine of A, we get x over b. And so if we just solve this equation here for y, we get y equals b sine A, and we get solving this one for x gives us x equals b cosine A. So we have found the coordinates of this point here to be, as you know, x comma y. So b cosine A comma b sine A from here. Now we know that the coordinates here are 0, 0 because that's where we place the triangle, right? We intentionally positioned it so that one of the vertices is at the origin. And of course, this one here, if this is the side C, that means this length from here to here is C, so this point will just be C0. Now what we'll do is we'll use the distance formula to find the distance between C and B, which is of course just A. So we get, from the distance formula, we get that the distance is going to be the square root of x2 minus x1 squared, quantity x2 minus x1 squared, plus quantity y2 minus y1 squared. That's just a direct application of the distance formula. Now, if we go ahead and square both sides, we get rid of the square root on this side, and we end up with a squared equals b cosine A minus c squared, quantity, and quantity b sine A minus 0 squared. If we square this using the f minus l squared law, so the game plan for solving these right triangles is going to be basically if you have the ASA or SAA situations, these refer back to the previous video. We're going to first find the third angle using this fact, because remember we have two of the angles, right? And then we're going to find the other two sides using the law of sines. For SSA or indeterminate case, we're going to first find the height. That'll help us determine the number of possible triangles. Then we'll find one angle using the law of sines. And the third angle we can just get from the sum equation for triangles, sum of the angles. And of course, we can get the third side once again by using the law of sines a second time. For the SAS and SSS cases, we're going to use the law of cosines to get the third side, because remember we have two of the sides. Well, in this case, the SAS, we have two of the sides. We'll first use it to get the third side. Then we'll find the smaller of the two angles using the law of sines, just because sines work out much better with those acute angles. And then the law of sines. And then for the third angle, we'll just use the triangle sum identity again. For SSS, we'll find the largest angle using the law of cosines. Then we'll find either of the remaining angles using the law of sines, And for the third angle, we can just use this. Okay, so that's basically where we're headed. All right, so here we have a problem that we should be able to handle with the law of cosines. Even though the ambiguity that can exist with SSA type problems, which we handle with the law of sines, does not exist with SAS type problems and the law of cosines, and therefore a sketch is not necessarily mandatory for these. A sketch, however, is always recommended with any mathematical problem that is geometric in nature, even remotely, because if for nothing else other than better intuitive understanding, we like to go ahead and always sketch these. So let's go ahead and look at this situation on a sketch. So we have angle A is 61 degrees, so we can just go ahead and let's try that better. Okay. And side B is 4 and C is 6. I could choose this to be either one of those, so we can go ahead and just let it be 4. And that means, since I've called this side 4, which is B, that means whatever angle we end up on this side here will be the angle B, and this angle must be C, so we'll go ahead and put the side opposite that as 6, which is C equals 6, and we should be able to get a good feel for this. Of course, we'll make this somewhat longer so that it's at least partially to scale. All right. So our triangle should look something like that, and we know that this is going to be B, and up here we have C. I do a little better job with this on an actual whiteboard, but this is as good as it gets for now. All right, and of course if I try to use a lot of fancy tools, the videos will just get too long. So all right, so we're going to go ahead and apply the law of cosines, and of course we want the sides B and C involved as well as A, but since we know the angle A, we're going to want to have that on one side, since the cosine that's involved on the other side of the law of cosines is going to be for that angle. So we're going to have A squared equals B squared plus C squared minus 2BC cosine A. All right, substituting the values that we know. A we do not have. In fact, if we look at the graph, we can see that we need A, and we also need these two angles to fully solve this triangle. So as we can see, we're right now on this stage, we're going to find the third side using the law of cosines, and then we'll work on the other the angles that are remaining using the law of sines. Okay, so we have A squared equals B squared, so that's 4 squared, plus C squared, so that's 6 squared, minus 2 times 4 times 6 cosine of A, which is 61 degrees. So basically A will be the square root of all that. So what we will want to do at this point is go ahead and bring up a calculator. As always, we'll check to make sure that we are in degree mode, so we seem to be okay. And then we'll just go ahead and type in second squared, which usually brings up the square root function. And then we have 4 squared plus 6 squared minus 2 times 4 times 6 times cosine of 61. It's highly recommended that every time you finish typing one of these into a calculator, you take a quick look to make sure you typed everything in correctly. 4 squared plus 6 squared minus 2 times 4 times 6 cosine of 61, and then we go ahead and hit enter. So we get approximately 5.36 if we go to 2 decimal places on this. So approximately 5.36 for A. And now we'll go ahead and find the smaller of the 2 angles that are left and use the law of sines. Of course, since 4, now we know there's no longer a question mark. We know this is approximately 5.36. So we can see that 4 is the smallest side, so we'll go ahead and start working with B and the law of sines. So we have sine A over A equals sine B over B. Always a good idea to write these without any kind of plugging in first, so that you don't make any errors. So sine A, that'll be sine 61 degrees over A, which is 5.36, equals sine of B over B, which is 4. So by cross multiplying, we end up with 5.36 sine B equals 4 sine 61 degrees. So sine B equals 4 sine 61 degrees over 5.36. So B will be the inverse sine of ditto. So all of that. All right, so now we'll bring the calculator back. And we'll go ahead and start with inverse sine. And then we'll type in 4. Actually, let's put all that into a parenthesis for best effect. So we'll put the numerator in parentheses, of course, after we push inverse sine. So second sine, we'll open parentheses, then we'll type 4 times sine of 61, and looks like we got too many of these. Let's get rid of 1. That looks better. Alright, so now we will go ahead and divide that numerator by 5.36. We'll quickly double check to make sure we typed it in correctly. So we get approximately 40.7 degrees on the angle B. Okay, so we now have angle B. It's kind of good to keep track of it on your sketch. That way you know exactly what it is that remains to be found, and we can see the only thing left is angle C. For that, of course, we don't need to use the law of sines or cosines anymore. We can simply use this fact that the sum of the angles, interior angles of a triangle is 180. So C is going to be 180 minus 61 minus 40.7, and you'll want degrees on all of those. All right, and when we do that, we end up with 78.3 degrees. All right, so we have all the values that we need, and we have officially solved this triangle because, as you see, we have all the values now. If we want to put in the last one, it'll look like that. That triangle where all the sides are now known and all the angles are now known is officially called solved. So the best way to make sure you're making progress, paper and pencil in hand, be doing these with me. You never want to watch a math video as if it's just a regular video, because math is completely interactive. That's how you learn mathematics, by doing it. All right, so let's move on and do another one. All right, as you can see, this is an SSS type of example because we have all three sides and no angles. So basically we need to start by finding one of the angles using the law of cosines, and generally speaking, going with the largest is the safest way to go. And as you know, the largest angle in a triangle is always opposite the largest side. So if we do a quick sketch here, we have a situation almost like that. So we can say this is A, this is B, this is C. Notice it's just recommended. Otherwise, you could solve for any of the angles and that would be okay. So this will be A. In other words, the law of cosines has that capability. This will be B and this will be C. All right, so if we want to solve for the angle C, we're going to have the side C squared on this side. So we get A squared plus B squared minus 2AB cosine of C. So we now substitute everything that we have and we work it out. But I want to show you just alternatively, rather than substituting and then plugging in and then solving for cosine of C, you could, if you like, solve for cosine of C first. So if you move this term to the left side, that always gives some good algebraic practice, and we're going to need that algebraic practice for the end of this lecture when we handle Heron's formula. So this will be a good kind of preview of that kind of thing. So we'll move that to the left side. We get 2AB cosine C equals A squared plus B squared, and we move the C squared to the right side so it becomes negative. So now we solve for cosine of C. So we get A squared plus B squared minus C squared over 2AB. So now we can plug in all the values that we have. From a mathematical point of view, this is preferred, doing it this way. All right, so we get cosine of C Of course, simply because of the practice that it provides. Otherwise, plugging in from the beginning can work too, and it's correct. Equals a squared, so 5 squared, plus b squared, which is 7 squared, minus c squared, which is 9 squared, and then over 2 times a, which is 5, times b, which is 7. Now notice that c could be either acute or obtuse. So how will we know if it's obtuse? Well, let's take a look at the unit circle real quickly. You know that on the unit circle, the angles that have a negative cosine are going to be in these two quadrants, correct? So if the angle that we find here for C is negative, if this cosine ends up being negative, then the angle is going to be in this region, which means it will be obtuse, because this is where the cosine is negative. So once we calculate the cosine here, we will know if it's going to be obtuse or not. So normally I like to just plug in C equals inverse cosine of all that. But this time, just for making this point, I would like you to see what happens when we actually calculate this. So let's go ahead and bring back the calculator. So we're going to open parentheses and type 5 squared plus 7 squared minus 9 squared. We're done with that. Now we can go ahead and exit out of that group of parentheses, and then we're going to divide by 2 times 5 times 7. We'll take 1 second to make sure we typed it in correctly, and then hit enter. And as you notice, we did end up with a negative value. So this tells you, before you even calculate it, that the angle C is going to be obtuse, meaning more than 90 degrees in this case. So since that turned out to be a nice rational number, we'll go ahead and use it, negative 0.1. If that turned out to be irrational, I wouldn't have typed in any kind of a rounded value. I would have just typed this entire fraction in for inverse cosine. So, but since that did come out nicely and a rational number, we can just go ahead and say C equals inverse cosine of negative 0.1. So now we're going to do shift. Okay, let's try it again. Shift cosine, and then we're going to type in negative 0.1. And so we get around 95.7 degrees for C. All right, so let's see what we have now. We have C here, 95.7 degrees. All right, so we can now use this value and the law of sines to go ahead and solve for either A or B. Take your pick, makes no difference. Let's just go alphabetically and use A. So we get sine C over C equals sine A over A. So now we substitute the values that we have. So we have sine of 95.7 degrees, It did not come out nicely. Over A, C, which is 9, equals sine of A over A, which is 5. Now, we'll go ahead and solve this for sine A. Of course, if I had stuck to my initial recommendation, I would have actually solved this for sine A first. It would have been cleaner, but this is pretty common, so it doesn't matter much. All right, let me go ahead and erase this so we get some space here. All right, so we get 5. Actually, let's go with the other one first. 9 sine A equals 5 sine 95.7 degrees. So we get sine A is equal to 5 sine 95.7 degrees over 9. So A will be the inverse sine of ditto. So we'll go ahead and type that into a calculator now. All right, so we want inverse sine of 5 sine 95.7, 5 times sine of 95.7, and we will divide that by 9. All right, we'll take 5 seconds to quickly check, make sure we typed it in correctly, and we should be good. All right, so we end up with around 33.6 degrees for A. All right, and of course, we only have to use the law of sines once. We could use it again if we really have a thing for the law of sines or anything like that, but otherwise it's not necessary, because look, we have here 33.6 degrees. We have 2 out of 3 angles of a triangle, so of course we'll just get B by subtracting those 2 angles from 180. And that should do it. So we'll start with 180, and we'll subtract from that 95.7, and then subtract 33.6 and hit enter. So we end up with 50.7. So 50.7, and again we've solved it because now we have all 3 sides and all 3 angles. That's all there is to solving using the law of cosines. Once again, because it doesn't have that ambiguity that we have with at least one of the cases with law of sines, tends to make these applications of the law of cosines a bit simpler. All right, no trigonometry class would be complete without covering Heron's formula for the area of any triangle as long as the 3 sides are known. It almost sounds too good to be true, because you are finding the area of a triangle and you're not needing any of the angles. Let that sink in and you'll see that that's pretty significant. We'll actually prove Heron's formula as well. So what Heron came up with is the fact that if you find for that triangle what's called the semi-perimeter, which is exactly what it sounds like, it's half the perimeter. Notice that if you have a triangle with sides A, B, C, If you add those sides, you get the perimeter, right? So when you take half of that, that's called the semi-perimeter. Then this formula will give you the area. So the square root of that semi-perimeter times that same semi-perimeter minus the first side, and again that's the semi-perimeter minus the second side times the same minus the third side. So this is really an amazing result because it doesn't involve angles at all. And so, I mean, let's just say you have a triangular plot of land that someone has just gifted you, and you just want to know the area, right? Well, all you need to do is go around that triangular piece of land or lake or whatever it is and measure the sides, and then you'll be able to calculate the area using Heron's formula. Now, while it's a really elegant and beautiful formula, getting to it is not as simple as it may seem. So let's take a look at the proof. I really wanted you to see the proof of Heron's formula because it shows you just how incredibly powerful algebra is and the significant role that it plays in all branches of mathematics. So if we just start with a triangle ABC with sides of length A, B, and C, we just learned by the law of cosines that we can write a squared equals b squared plus c squared minus 2bc cosine A. Now, if we go ahead and solve this equation for cosine A, we can move this to the left side and it becomes positive. So 2bc cosine A equals, and we'll move the a squared to the right side and it'll become negative. So we get b squared plus c squared minus a squared. Now we divide both sides by 2bc. We get cosine A equals b squared plus c squared minus a squared over 2bc. We know that S, which is the semi-perimeter, is 1/2 of a plus b plus c. So if we multiply both sides by 2, we end up with 2s equals a plus b plus c. Now if we subtract 2a from both sides, we'll end up with b plus c plus a minus a equals 2s minus 2a. Now, if we do the same thing we just did by subtracting 2a, repeat the process and subtract 2b one time and also subtract 2c another time, we'll also end up with these two expressions. A minus b plus c equals 2 times s minus b, and a plus b minus c equals 2 times s minus c. You can see some of these elements of Heron's formula starting to pop in, correct? So also note that 1 minus cosine A can be written as 1 minus this expression that we obtained for cosine A. So it becomes 1 minus that expression. Now we need to go ahead and combine those. We have a common denominator of 2bc, so we get 2bc plus a squared, because minus times minus will give us the positive here, and then these two both become negative because of that negative. So we end up with this expression. Now this is what I meant by the amazing power of algebra. So if we go ahead and factor out a negative from this term, and that term, because if you recognize it from algebra, those look like the makings of a perfect square trinomial. Then we can factor that as quantity b minus c squared, and then we get this. So now, if you recall, now we have a difference of squares, which is going to be, if you recall, the rule was f squared minus l squared equals quantity f plus l times f minus l. So applying this rule, one second. All right, we're back. So applying this rule to this expression gives us first minus second, that's what this is, first plus minus last, times first plus last. The order of these does not matter. And then over 2bc, of course, because of multiplicative commutativity. All right, so we go ahead and distribute the negative, so we get a minus b plus c times a plus b minus c over that. So notice that this expression here, a minus b plus c, we had seen it before. It's 2 times s minus b, and a plus b minus c is 2 times s minus c over 2bc. So we have this new expression for 1 minus cosine a right there. Now we want to go back to an old friend of ours, which, well, two old friends of ours. The double angle identity for cosine in two different versions of it. The first one was 2 cosine squared theta minus 1, and we're going to make a substitution. We're going to let theta be a over 2, which means, of course, 2 theta multiplying both sides of this by 2 is going to be a. So instead of 2 theta, we can write a, and instead of theta, we can write a over 2. So this expression now becomes this, and if we add a 1 to both sides, or actually just move the negative 1 to the other side, which is basically the same as adding 1 to both sides, we end up with 1 plus cosine a equals 2 cosine squared of a over 2. So if you recall, we had actually derived, not driven, we had derived a formula for 1 minus cosine a, and you could also, in a very similar manner, show that 1 plus cosine a, if you go through the exact same process but with a plus, it will simplify a different way into this. So now we have 1 plus cosine a equals 2 cosine squared of a over 2, and we can now replace the 1 plus cosine a with this expression. So we have this. Now, if we divide both sides by 2, we end up with s times s minus a over bc equals cosine squared of a over 2. So that means cosine of a over 2 is going to be the positive square root of s times s minus a over bc. In case you're wondering why the cosine of a over 2 will be positive, remember, a is an angle in a triangle, so there's no way it can be larger than 180. In fact, it's going to be less than 180 because all the three angles have to add up to 180. Even if you have a very extreme triangle where one angle is like 179.9 degrees, it's still not going to be quite 180. So that means a over 2 itself will be less than 90. So, and we know that for angles that are between 0 and 90, the cosine will be positive. So that's why this is the case. And of course, the sine will also be positive later because of the same reason. In fact, sines are positive all the way from 0 to 180. So a over 2 will definitely have a sign that's positive as well. So on this other side, we're going to do a very similar thing, but we're going to do it with the other version of cosine 2 theta, which is 1 minus 2 sine squared theta. So we get cosine a equals 1 minus 2 sine squared a over 2 using these substitutions. And this time what we want to look at is 1 minus cosine a, which becomes 2 sine squared a over 2. Remember, you can just move this to the other side, becomes positive, move this to that side, becomes negative. So we just switch the sides, that's all. So now we know 1 minus cosine a, we derived it here. So we have 2 times s minus b times s minus c over bc equals 2 sine squared a over 2. And now again we can divide off the 2's and we end up with this equation, s minus b times s minus c over bc equals sine squared a over 2. So that means sine of a over 2 is going to be the square root of s minus b times s minus c over bc. But we also learned in the last video that you can find the area of any triangle. That was another universal formula that we found, as long as you know two sides and the angle between them using this formula, 1/2 BC sine A. Now if you double both sides, you get 2A equals BC sine A, or sine A equals 2A over BC. So one old friend of ours was the double angle identity for sine, which gave us 2 sine theta cosine theta. So if we replace the 2 theta with a and the theta with a over 2, we end up with 2a over bc equals 2 sine a over 2 cosine a over 2. Notice we have found expressions for cosine a over 2 and sine a over 2 in these radical forms. So we get 2 times the square root of this item right here times this one. So now notice that these two are both square roots, so you can multiply under the radical and you get s times s minus a times s minus b times s minus c over b squared c squared. And also we can get rid of the 2's and we can split up these because this is a perfect square, so we just get square root of s times s minus a times s minus b times s minus c over bc. Notice we have the same denominator, just multiply it on both sides and it'll go away. You end up with a equals exactly what we were hoping to get, and that's Heron's formula. Now this is a beautiful proof. Of course you're not going to be responsible for reproducing this on a test, but nevertheless it will do you an unbelievable amount of good if you actually decide to sit there and do the proof on your own without any help. That is the kind of effort that will set you apart from the pack, so to say, and will lead you toward a different path as far as mathematics is concerned. All right, so I hope you enjoyed that as much as I did. I've seen this many times, the proof of Herons. I've done it many times, but one thing I've never seen, which is going to be unique about what I did here for you, is that I did it all on one screen or one page. It's so long that usually when you look in textbooks, it's done over 2 or 3 pages, and you have to keep going back, forth, you know. So my goal was to get it all on one screen for you, which thankfully I was able to accomplish. All right, so let's go ahead and apply Heron's formula, and that will be it. That will be the last thing we're going to do in this particular course. Of course, compared to the proof, this is going to look like a vacation in Maui. So we just need to know the formula. We have the 3 sides, so we know that according to what we just learned, a is going to be the square root of s times s minus a times s minus b times s minus c. Now we can go ahead and say a is 12, b is 16, c is 25. So we can go ahead and calculate s, which is going to be the semi-perimeter, so 1/2 of a plus b plus c. So it's going to be 1/2 of 12 plus 16 plus 25. So 0.5 times 12 plus 16 plus 25, 26.5. So that's the value of S. And now we can quickly get the area by starting with S, 26.5, and then times S minus A. So 26.5 minus 12 times 26.5 minus 16, and lastly 26.5 minus 25. All right, so we end up with, we don't need to do any of that. We can just type it all in one shot. So we're just gonna carefully type it all in. So we're gonna get second square root, and we start with 26.5 times quantity 26.5 minus 12 times quantity 26.5 minus 16, and then here we needed a parentheses, so let me clear that. All right, this calculator is a little bit touchy, I have to be careful. So times 26.5 minus 16, and then we need to get out of that parentheses, and then times 26.5 minus 25. All right, so we quickly check to make sure we didn't make an error. 26.5 times 26.5 minus 12 times 26.5 minus 16 times 26.5 minus 25. All right, so we can go ahead and hit enter, and there we have the area of this triangle. So 77 point almost 8. And of course this will be in square feet. Notice that the units do make sense because each of these has a unit of feet. So when you multiply 4 of them, you get feet to the power of 4, but then when you take the square root, you end up with square feet. And that pretty much wraps it up for Heron's formula, and also for our trigonometric lectures. So I hope you've enjoyed them and you've learned something in this class, and I wish you great success throughout your life, and hopefully we'll see you in another class. Be safe.